Hello everyone. So today we are going to discuss the closure axioms in topology. See, these are the closure axioms and now I am going to prove why they are true. So what does number 1 say? Number 1 says that the closure of phi is phi. So why is this true? See, I know that phi is both closed and open. That means clopen. So that means phi is closed. And so phi closure equals phi. There is a result that if a set is closed, then it is equal to its closure. So if you want me to prove that, I can prove it right now. So okay, let me first prove that. A is closed if and only if A is equals to its closure. So how do I prove the first part? See, let A equals A closure. By definition, A closure is a closed set, right? So that means what? A is closed. Why? Because A closure is closed. Now for the converse part, let A be closed. Now I have assumed A to be closed and I want to show that A is equals to A closure, right? Okay. Now since A is closed, what can I say? I can say that A complement is open. And let me assume that there is a limit point of A which is not contained in A. That means there is some limit point of A which lies in A complement. So by definition of limit point, what do I know? I know that every open set which contains the limit point, if I take the deleted neighborhood from that and take the intersection of A with that, I will get non-empty intersection. Now A complement is open and X belongs to A complement. So A complement minus singleton X. If I take the intersection with A, I should get non-empty intersection. But is this true? No, this is not true. Why? Because A complement is completely outside of A. So no, it doesn't matter if I neglect some singleton set or anything, it will always give phi. So this is a contradiction. So what do I got? That X is not a limit point. That means what? Our assumption was wrong and that every limit point of A must lie in A. If every limit point of A is contained in A, what does that mean? That means the derived set of A is subset of A. Right? If every limit point of A is inside A, that means the derived set of A is a subset of A. Why? Because derived set is the set of all limit points, right? Okay. Now see, the derived set is inside A. If I take A union, then what do I get? A union A derived set, subset of A. I have taken A union both sides. A union A is A, and here I got A union derived set of A, and this is nothing but A closure. This is A closure. I got A closure a subset of A. But by definition, I know that A is actually a subset of A closure, right? But A is a subset of A closure. So, if two sets are subsets of each other, what we can say? We can say that they are equal. So, here is the proof that why a set is closed if and only if it's equal to its closure. Okay, so we have proved the first part. Second part is similar. Why is x closure equals x? Because x is clopen. It means x is closed. Simple reason. Number 3. I have to prove this. How do I prove this? See, I don't know whether A is closed or not, but A closure is always closed by definition. And just now I proved that if a set is closed, then it will be equal to its closure. So the closure of A closure will be A closure. Right? So the first 3 proofs are immediate from the first proof. Now the fourth part. I have to show that if A is a subset of B, then A closure is a subset of B closure. See, what I am going to do, I know that B is always a subset of B closure, isn't it so? I know that, and it is given that A is a subset of B. Again, B is a subset of B closure, so that means what? A is a subset of B closure, right? And B closure is what? B closure is closed. It is closed superset of A. But what do I know? Of all the closed supersets of A, the smallest closed superset is actually A closure, right? So what kind of relation is there between A closure and B closure? If A closure is the smallest closed superset of A and B closure is any arbitrary closed superset of A, then A closure must lie inside B closure. That means A closure should be a subset of B closure. Now coming to our last proof. See, I know that I have taken, if I take a union of any two sets, then each of those sets will be subset of the union. That means A is always a subset of A union B and B is always a subset of A union B, right? Both these things are true. And just now I proved that if A is a subset of B, then A closure is subset of B closure. So from here we can say that A closure is a subset of A union B closure. B closure is a subset of A union B closure. So if I take the union of any two subsets of a set, then that will also be a subset, right? A closure, B closure, both are subsets of A union B closure. So their union will also be a subset of A union B closure. And now for the second part, I have to show that A union B closure is also a subset of A closure union B closure, right? Okay, so why is that exactly true? See, to show A union B closure subset of A closure union B closure. I know that A is a subset of A closure, B is a subset of B closure, right? That means what? A union B subset of A closure union B closure. Again, something is subset of another, that means this closure will be a subset of this closure. Now, have you noticed one thing? A closure union B closure is the union of two closed sets. And what do we know? The union of any two closed sets will be a closed set. So A closure union B closure is closed, and since it is closed, if we take its closure again, that will be nothing but A closure union B closure. This is 2. Here from 1 and 2, what do we say? Okay, so here we have proved the closure axioms, and in the next video we are going to discuss the interior, exterior and boundary. Thanks a lot.